Hello and welcome to York Observatory monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alani Carswell Observatory, located at York University in Toronto, Ontario, Canada. Your TeleTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time right here at our YouTube channel. Sorry. At our YouTube channel. For any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle Yorku Observatory. We would like to inform you about the Summer 2025 Astronomer in Residence program. This program is a collaboration of the Alani Carswell Observatory with Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney, to lead in-person presentation and shows using the park's observatory. This week, observatory members Sona Withers and Anna Skrinick are at Killarney, almost wrapping up their time as astronomers in residence. To learn more about the program and check their blog, visit our website at yorku.ca/science/observatory/air. Good evening, everyone. My name is Hector Jimenez, and I am here alongside Denel, Anidia, and Zach from Alani Carswell Observatory at York University. We're excited to welcome you tonight, especially because we have got a fantastic guest speaker, Maxime van den Moortel, who will be diving into an incredible topic, the mysteries of black holes. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation and the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now, let's see what targets are up tonight. Please, Anidia, go ahead.
Welcome, everyone. Before we get started with our main show, we want to give you a little update on what you can see tonight. So, in Toronto, around 11 p.m., you can see objects like Arcturus and Andromeda. It has particularly been not a very good summer to view planets, as all the planets have set way before it's dark outside. But make the best of what you've got and make sure to look at these targets and get your astrophotographies in. I will now pass the platform to Danelle, who will introduce our wonderful guest speaker for tonight. Thank you.
Good evening, everyone. It is my pleasure to introduce tonight's guest speaker, Maxime van der Moortel. Maxime has always been fascinated by the large structures of the universe, especially mysterious objects like black holes. In 2019, he earned a PhD at the University of Cambridge in the Department of the legendary Stephen Hawking, and subsequently held a postdoctoral position at Princeton University. Today, he's an assistant professor of mathematics at Rutgers, the State University of New Jersey, where he investigates the secrets of gravity using differential equations to understand what happens inside these incredible black holes. Please join me in welcoming Maxime van de Moortel. Thank you for being here with us this evening, Maxime. The floor is yours.
Thank you very much, and thank you to Hector, to Daniel, and to Anidia and Zach for the invitation. So let me share my screen. And you can see my screen, right? Okay. So indeed, I'm a mathematician working on black holes, and it's in fact the first time that I speak in an observatory. So it's a really great pleasure to be here with you all. And so I wanted to give a gentle, non-technical presentations about one of my main topics of research, which are black holes. So first of all, because I'm assuming we have a broad audience, I want to recall what black holes are. So here I put on display an image of a black hole that was generated by a computer. As you can see, there's a dark sphere in the middle, that's a black hole in itself, and around this some accretion disk. So I will come back to this picture in a second, but I want to explain, first of all, what are black holes and how they are encountered in nature, because black holes are indeed objects that can be observed, and this is something that's very important both for astronomers, theoretical physicists, or mathematicians like me. The second part that is also very important to me is what role they play in our understanding of gravity and space and time, on the one hand, and what are the big mysteries that we haven't solved yet and that we want to use mathematics, observations, or computer to try to solve and to understand a bit more about these enigmatic objects. And I will finish with my personal favorite, which is a question that I've been working on for now almost a decade, which is trying to understand what happens if you fall into a black hole. I think this is a question which is both very concrete, because this is a scenario that can happen to either of us, or maybe hopefully not, but falling into a black hole, what happens, right? And it's also a question that is of incredible mathematical depth. It turns out you need a lot of mathematics to answer this question. So I will try to give my take on this. And please interrupt me if there are any questions. I know there are some people watching live, but if there are any questions, I would be happy to answer them. So, so what is a black hole, first of all? So let's just talk about the name in itself. So black. So why is it called a black? It's because it's a celestial body. So let's say a star towards the end of its life, from which matter or light cannot escape. The gravity pull is so dense near a black hole that light cannot escape. So light is trapped, if you want, inside a black hole, and that's why from the outside it looks black. Okay, it doesn't mean that once you're inside it, you maybe see some rays of light, but from the outside it looks black, and so this would literally look like what you see in this picture, which was also computer generated. So now the paradox and amusing fact is that black holes, even though technically speaking they are black, but there is all sort of matter orbiting around, which is very luminous. So in fact, you may be able to observe what's right outside of a black hole, although the black hole itself will be black. So a common misconception about black holes is that they are massive, that they are humongous. And in fact, at the scale of other astrophysical bodies, they're actually quite small, they're quite tiny. So to give you an idea, so they're extremely massive. So for example, if you take a stellar black hole, so a black hole that results from the death of a star, an order of magnitude would be about 20 times the mass of the sun for the smallest one. So that's extremely massive, of course. But the diameter would be about 20 kilometers, which is extremely small if you think about it. So the Earth, the radius, I think, is about 47 kilometers. So if you look at a stellar black hole and you compare to the size of the sun is much bigger. So the black holes are tiny. And this is really something that is not very well known among the general public. So since we're in Toronto in the observatory, Toronto is a city I know pretty well. I've visited many times, and I know you have this impressive CN Tower in the center of Toronto. So let me make the following comparison of scale. Okay, imagine a bug crawling on the floor like an ant. Okay, under the CN Tower, right? So the ant would be the size of the black hole, and the CN Tower would be the size of the sun. It's about a factor about 100,000 times bigger. The sun is bigger. The black hole is tiny. So maybe this is, if you're interested in this black holes, but you are not a scientist, this is maybe one of the takeaways. That black holes are actually quite tiny, very massive, very dense, but very tiny. So with that being said, there are some black holes that are bigger. Actually, they are still small at the scale where they are, but they are bigger than the black hole, the stellar black holes, and those are the black holes at the center of galaxies. So in fact, our own galaxy, you might know, the Milky Way, has a black hole, Sagittarius A star, in its center. So this one is much more massive. So it's 4 million solar masses, right? So it's millions times more than the stellar black holes. But it's still small compared to the size of the galaxy. That's also an important point to make. And the other common misconception is that people may think that black holes are quite rare, that these are very, we only find them in very special circumstances. But actually, astronomers believe that they are quite widespread, and that probably a lot of galaxies, if not most galaxies, actually have a supermassive black hole in their center. And this is still something that is at the heart, as far as I understand, of observations, trying to understand how they form. This is still an active research topic, and maybe some people in the audience know much better than me, know this topic much better than me, so I will move on. So what I want to emphasize is that the story of black holes is a story where the theory meets the experimental. And this is something that I'm very happy to discuss at an observatory, because the theory of black hole in reality started, I think, from the conceptual revolution of Albert Einstein. And this is why he's dressed as a revolutionary, because his ideas, are scientifically very radical. The first one, which doesn't sound so radical, is that the speed of light is an absolute constant in vacuum that does not depend on the referential, and nothing goes faster than that. So this is an idea that has been well known now. I think a lot of people accept it. But the consequences are very radical, because then it means that time is not absolute. So think about it. We've been doing science since Isaac Newton, and even before Galileo, 500 years ago, saying that time is an absolute clock for everybody. And all of a sudden, time actually depends on the observer. And the moral of that, and this is something that I really want to spread, in broader, is as broad audience as possible. The moral of that is that you have to think of space and time together in a single entity that is called space-time. And this is what Einstein taught us with his theory of special relativity, 1905, so 120 years ago. The second revolutionary thought of Einstein is that gravity is not a force in the sense of Newton, meaning an instant interaction between particles that attract each other. It comes from the geometry, and more precisely of the curvature of space-time. So these words at the time of Einstein were very new, because we were only starting talking about geometry of space, and now we even have to talk about space and time together. So this was a very revolutionary idea. And I want to tell a little story. So I don't know, maybe on the YouTube stream, maybe there are some high school students that are watching us, and maybe for some of you who are freshmen, high school was not a long time ago. For me it was, unfortunately. I want to tell you a little story about Albert Einstein when he was in high school. So he started thinking that if really the speed of light, obeys Galilean relativity, which has been known for 500 years before him, then if you can run at the speed of light, you would see that the beam of light would be frozen. So there would not be any electromagnetic wave, as in the theory of Maxwell. And he observed that the theory of Maxwell does not account for any such phenomenon. So that sounded very strange to him. And so you see, it was already sort of, kind of a revolutionary thought, because he was already thinking that there's something wrong when trying to combine electromagnetism and the mechanics of Galilean relativity that were known at the time. So what is the moral of the story? And maybe, we have a lot of young minds maybe watching us, is that, do not be afraid to question the rules, especially the theories that are taught to you, by having this kind of thought experiments, because it's when you're being critical that you can actually make new science, and particularly make new physics. And this is what Einstein has been doing his whole life with the success that we know. So moving on from this little story, I want to come back to Einstein when he was already a little older. So that is he was in his 30s, when he invented the theory of general relativity. So general relativity is an idea, is a theory that relies a lot on mathematics, and the mathematics that it uses are somewhat advanced. I mean, meaning, okay, maybe graduate mathematics, but the underlying ideas are physically very simple and powerful. And I've been studying this theory for about a decade, as I told you. So I think I'm well placed to tell you that it's actually more simple than you think. And, in my opinion, perhaps even more simple than other theories in physics, such as quantum mechanics. So the base idea is very simple. It says that gravity is not a force. It comes from the curvature of space-time. So an imperfect analogy that you can do to understand this, that you can make, is to think of space-time as a fabric. So it's an imperfect analogy, but okay, it's good enough for a first exposure. And this fabric is being bent by the presence of matter. So here you see the sun. It's a very massive piece of matter, right? And it digs this well. And the Earth rotates around the sun because it has to follow the curvature created by the sun. And the Earth, of course, also creates some curvature at its level, but that curvature is much smaller, so it doesn't really impact the sun as much. So me being a mathematician, I cannot resist showing you the equation, but I promise I won't be technical. I think even if you don't understand the details about an equation, it's very useful to see that there is an equation. And for gravitation, general relativity, there is an underlying equation, which was formulated by Einstein, which is now called the Einstein equations. And this equation basically formalizes the idea that I just mentioned. So the main unknown of that equation is a metric G, which encodes everything about space-time. So what is a metric? It is an object that measures length and time. So there is a mathematical definition, which I invite you to consult if you're interested. But for now, let's just think this is like a grid. Okay, you see here you have a grid, you have squares, so you can measure length. Imagine that you can measure also length and time at the same time. Okay, this is what this object does. And it tells you everything you need to know. And the distortion of space-time is encoded by its curvature, which is the left-hand side of the Einstein equation. So this left-hand side, this is what Einstein called the marble. This is really the noble part, the part that is fundamental in his theory. And then in turn, that curvature of space-time is created by matter, which is on the right-hand side. And here this T stabilizes the energy of the matter, and then there are some constants. And so the beauty of it is that this matter term can regroup anything. It can regroup electromagnetic wave, fluids, solids, whatever you want. Okay, this is on the right-hand side. And this is what Einstein called the wood. Okay, this is the part that is the least important, the least noble. So if you believe in the theory of general relativity, you believe that essentially everything about gravity is contained in this equation. Now, okay, there are maybe some outliers, like dark matter, but let me conveniently swap those under the rug and not talk about them, because I don't think I understand what dark matter is, like a lot of people. So let me stick to this equation for now. So what did people do with this equation? So maybe this is something that has little appreciation. So let me explain a little bit. So you have an equation. You can try to find some very simple solutions, some solutions that are very explicit. So for instance, one such solution is a completely flat solution, the boring solution where nothing happens. There's no matter, there's no curvature, nothing. Okay. So that's one solution. You have also other solutions like that. But this procedure becomes very limited because you understand that trying to write an exact solution requires a lot of symmetries, a lot of miracles in the calculations, and so you get an access to a very small set of solutions. So very quickly, people have started moving on from this. So what can we do now if you are a scientist who wants to understand the Einstein equations? So one solution is to simulate the solution on the computer. And this has been extremely fruitful with really beautiful both images and result in numerical generativity. It's very complex, but it really gives rise to many successes. So this is not, I'm not a specialist of that, so I cannot say much more, but I know that there's very interesting research, very current research in that direction. What I want to tell you about what I'm doing is a mathematical approach, which is a little bit like the computer, but except that we are writing a bit more explicitly. So if you want, it's a bit of an in-between between the historical approach and the numerical one. So instead of looking at one particular exact solution, we can look at perturbations of those solutions and try to control what these perturbations are doing. And, and sometimes things get very subtle, in fact. And this is where really you want, the whole power of the mathematical formalism allows you to understand more physical phenomena. So it is rigorous, it is proof-based, you prove theorems, but the point is not at all that it's rigorous. That is not the point. The point is that behind these mathematical techniques, there is more physics that is being uncovered, actually, which is not accessible through, the more rudimentary methods, which are trying to find explicit solutions. So if you have a richer theory of generativity as soon as you're ready to embrace these techniques that come notably from differential equations. So this is really what I do in my day-to-day research. Sometimes people ask me, what do you do? And they don't really understand how a mathematician can sort of sit, at the desk and write theorems. So I hope I conveyed how these theorems can actually shed some light on actual physical phenomenon inside black hole. So a talk on generativity would not be complete without talking about the gravitational waves. So this is really where the beauty of the theory meets the experimental. Because if you look at the Einstein equation and you're any self-respecting mathematician, you immediately see that these are wave equations. So what does it mean? It means that if you have a small perturbation in the space-time, a small ripple, it will propagate like a wave at the speed of light. And this is what people call gravitational waves. It's as simple as that. So here you see an image. You have like two neutron stars. They orbit around one another. And as you can see, they make ripples in the space-time, and those ripples propagate. So it's been a while since it's been predicted that the Einstein equations do this, but these gravitational waves are notoriously very difficult to observe. And we had to wait until 2015, coincidentally exactly a century after the Einstein equations were formulated, for them to be observed. And I can tell you, I was a PhD student then, and this was announced in the amphitheater, when I took a class in black holes, and this was really a historical moment. So there was this famous LIGO collaboration that I'm sure a lot of people in this audience know. And this LIGO collaboration were finally able to observe the gravitational waves, and that gave rise to a Nobel Prize, as many of you know, in 2017. So what's beautiful about this experimental breakthrough is that not only it gives us a new way to watch the universe, to do experimental astronomy, but it also gives a spectacular validation of the theory of generativity and of black holes, because these waves were actually emitted by black holes. So moving on, I actually want to talk about black holes and mention one of my scientific heroes, Robert Oppenheimer. So you might have seen there was a movie about him. Unfortunately, he was not famous for his work on black holes. You might have heard he has work on some other things that I don't really want to discuss in detail today. What I want to talk about is this small paper from 1939 about gravitational collapse. So this paper is very surprising because it has all the ingredients of the modern understanding of black hole, even the way we conceive it mathematically, but it was very ahead of its time. It was in 1939. And if you look at the date, it was published on the 1st September 1939. So let me ask the audience and maybe some of the organizers, do you know what happened on September 1st, 1939? If anybody is awake.
No, I don't know.
No. So on September 1st, 1939, this is the first day of the Second World War, actually. So this is the day that Hitler invaded Poland. And so very quickly, all these people, Oppenheimer in particular, they moved to military applications. And this paper was completely forgotten. It's a bit of a tragedy of science, actually. The paper was completely forgotten, even though he got everything right, basically. And it was only rediscovered 20 years later by Finkelstein, and then only much later by Penrose, actually. So it's quite interesting how history panned out, actually. It's basically lagged, black hole science for like 20 or 30 years because of the exact historical timing. So what is done in this paper? So this is quite interesting. So this is a scenario that's a little bit physically dubious because it looks at the gravitational collapse of a ball of dust. So dust, every self-respecting physicist would not look at dust, right? I mean, dust is a fluid without pressure, so it's not very physical. But it explains how this ball of dust can collapse into a black hole, and everything is correct about this paper. I mean, so it's both mathematically and physically correct. Even now, it could almost be considered a mathematical paper, actually. And the paradox of this, and I guess I'm not really, preaching to my own choir there, is that Albert Einstein, the very same year, posted a mathematical paper in which he thought he proved that black holes are impossible. And this was published in a very good, prestigious Journal of Mathematics of Princeton, which are the Annals of Mathematics. And so the irony is that both the math and the physics of that paper of Einstein are completely wrong. So, of course, the theorem is completely false, and the physics is very misguided. And so it's funny that Oppenheimer completely ignored that paper, even though Einstein was already an authority at the time, and just did, this breakthrough without really acknowledging the fact that Einstein said it was impossible. So I think, this is quite, it shows you that, history of science is not smooth, right? I mean, there are a lot of very interesting things that happen there. So of course, now we have a better understanding of how stellar black holes at least form. And again, I'm by no means an expert on this. So, I'm very humble to speak about this in an observatory where some people know much more, but let me give it a shot. So we know that most stars, they generate during their many sequence, they generate energy through the fusion of hydrogen into helium. So this is what happens for our sun. But eventually hydrogen runs out, and then it's replaced by other elements until everything runs out. And then there's no mechanism actually to prevent the collapse of all this gas onto itself. So this is what gravitational collapse is. I mean, if you don't have anything if you don't have any energy, you just have particles of gas that just attract each other and then they collapse. And that is why black holes are so small, because all this matter has been shrunk into a very small space. And so now we know that if a star is massive enough, after it goes through its main sequence and becomes a supergiant, it can eventually become a black hole through gravitational collapse. And we understand this phenomenon both of, observationally, I believe, and also mathematically very well. So now I want to attack another misconception about black holes. And one of my scientific heroes who helped clarify this is Martin Kruskal, who is my late colleague at Rutgers University. There were other very important people in this story, such as Georges Lemaitre, Belgian priest, or Eddington Finkelstein. Finkelstein and Eddington. But let me talk actually about Kruskal, because, well, he was a colleague of mine. So the important point is that if you go into the black hole, there's this point of no return, which is the event horizon. So once you pass the event horizon, this is a moment where you cannot escape the black hole anymore. And in fact, even light cannot escape. So this is really what marks the boundary of the black hole, if you want. And for a long time, it was a very, very big misconception. What happens when you cross this event horizon? So people thought that something horrible happens, singularity, and this idea comes back periodically. But this is false, actually. So in fact, nothing happens to an observer when you cross the event horizon. And to see that, you have to know a bit of geometry. You have to find the right coordinates. And Kruskal was one of the ones who found this system of coordinates. So the irony is that it's called the event horizon, but in reality, it should probably be called the non-event horizon, because when you cross it, you don't even know that you've crossed the event horizon. In fact, you would need to know the whole history of the black hole before you're able to know this. In fact, it's very much a non-event when you enter a black hole immediately. That is when you pass the event horizon. But what happens in the interior, so further down after the event horizon, towards whatever is the end of the black hole, that is another story, which is still an active research topic that I want to now talk about. So the simplest model in which to study this is that of a spherical and time-independent black hole. And in fact, this is quite a coincidence. This was found only a few months after Einstein set the Einstein equations by Schwarzschild in 1916. And this was done in very peculiar circumstances because Schwarzschild was actually at war. It was during World War I, and he was on the front lines. And so very tragically, Schwarzschild died before his paper could be published. So Einstein had to take the paper and submit it himself in the name of Schwarzschild to the Prussian Academy of Science. Einstein really defended that paper. But that paper actually did not talk, it was not a paper about black holes, ironically. It was a paper that Einstein and Schwarzschild both thought it was describing a star, just a star, the exterior of a star. Because if you look at the Schwarzschild paper and you read between the lines and you adopt a bit of a revisionist approach, you see that it has a singularity inside. So this is your black hole on the left. Okay, this is the event horizon. You cross, and once you get to the middle, okay, then you see that the observer gets infinitely elongated, which is something that physicists who have a very good sense of humor call spaghettification. And because of this, so this is of course a singularity. This is a region of spacetime where curvature becomes infinite. Black holes were rejected by Einstein and many of is contemporaries. Said that, well, I mean, this even said, to Lemaitre, who had also identified this, he said, your physics, sir, your mathematics are impeccable, but your physics are abominable. And the reason is that it said, well, there cannot be any singularities in nature, period. This is basically what was said by Einstein. And he said, well, the singularities must be due to the fact that this solution is too symmetric. It's perfectly spherical, it's round. So if you perturb a little bit the sphere, which you should be able to do in nature, right? After all, there are all sorts of perturbations. Nature is not perfect. Then you won't have any singularity. And boy, was he wrong. And this is basically for proving that he was wrong. That there was a Nobel Prize in 2020. So the 2020 Nobel Prize I really like because it celebrated actually black holes. So on the left, you have two astronomers, which I'm sure many of you know, who have made some breakthroughs in observing compact objects at the center of the galaxy that are now constituted to be, the supermassive black hole inside of the Milky Way. But I want to tell you about this guy on the left, Sir Roger Penrose, who I had the pleasure to meet. And Penrose is a mathematician, and he proved, in fact, a theorem. And the theorem is extremely simple, but also very influential. His theorem, which is called the singularity theorem, says that if you perturb the Schwarzschild black hole, let's say, or any black hole for that matters, so see this perfectly spherical thing, you perturb it a little bit, you make it having a bit of a non-spherical part, then there is still a singularity. And so this is the doom of Einstein's dream to reject black holes on the ground that they are singular. Singularities are, in a sense, stable to perturbations. You're not going to get away by just saying that these are mathematical artifacts that have nothing to do with nature, because those are actually stable, and then the rest is history. This is how theoreticians started to gradually accept the existence of black holes. Then there were these observations that were consistent, and all of a sudden, the whole of physics believed that black holes were indeed real objects, not just some mathematician's fantasy. Right? So the singularity is actually not due to the perfectly spherical character, which was a very big conceptual feat in reality. So now, okay, but what is a singularity inside of realistic astrophysical black holes, such as the stellar black holes that are near us? Well, I mean, first of all, you have to account for the fact that real black holes are not spherical. They're not perfectly spherical. They are also not perfectly time independent. So the whole thing is a bit of a mess, right? I mean, so it's created dynamically, through the collapse of a star. So there are a lot of things that happen. But it seems, at least, based on the research I've made, it seems that there are the following patterns that you can observe. And here for you, I have drawn the diagram of a black hole. So this is a diagram in space and time. And here are the trajectories of two observers. Okay, so there's this observer in red and this observer in purple. So you see this line here, that this first diagonal line that you see here, this is the event horizon of the black hole. This is a point of no return. And depending, so the red observer is a little bit earlier than the purple one. The purple one arrives a bit later. So depending on how late you are, you will observe, you will have a different fate, and none of which is going to be very nice, I'm afraid. So if you fall quite early into the black hole, you will encounter a strong singularity, and you will be infinitely crushed. So it's a bit similar to what happened with Schwarzschild, what you had here, except that here for Schwarzschild you are spaghettified. Here, most likely you will be crushed, in fact, but it's still, it's still an infinite deformation. On the other hand, an observer that arrives a little bit later, what happens is that they get actually burned by infinite energy, which is not quite the same as being crushed. Okay, it's still either way, it's not a very nice fate to fall into the black hole, I'm afraid. But nonetheless, this tells us something quite fundamental regarding the singularities inside black holes, at least in classical general relativity. So this, I think, this picture, this is, a research program that I'm in the middle of completing, trying to prove that this is indeed what happens, at least in certain circumstances for the Einstein equations. I think this will give us a very definitive vision of the singularities that can happen inside black hole in classical general relativity. Now, this will have some relevance, of course, for the observers that fall into the black hole. But there is also, growing interest in trying to understand what happens at the quantum level, and there I cannot omit to mention the late Stephen Hawking, which I also had the pleasure of meeting during my time in Cambridge. Unfortunately, he passed away when I was still a student there. And with Roger Penrose, they worked together on singularities, and Stephen Hawking made a breakthrough, which is this so-called Hawking radiation. It's an argument that indicates that black holes actually evaporate through quantum effects. And there are many interesting questions in trying to understand what is inside of the black hole in this case. Are the quantum effect importance? And right now, all I can say, if you ask me further questions about this, is that I don't know. Because for now, I think the mathematical formalism is not quite ready for this. So this is something we're still developing. But I have very good hopes that the mathematical formalism within maybe 5 to 10 years will be ready to then tackle those questions. And then, I'll be happy to take all your questions then. So I'll give you a rendezvous in 10 years. So let me finish with a little joke. So it's a joke that was funny a century ago. I mean, nowadays it's only relatively funny. But to finish off on a more serious note, I think one of the biggest dramas of science is that we think in a way that is too Newtonian. We think that time is universal and that there's a universal clock for all the observers, and we should maybe think in a bit of a more relativistic way, and trying to sort of understand that time depends on the observer, and to try to think even in our daily life as space and time as being sort of one and the same. And I think if we start to adopt this viewpoint even very early on in education, then this would be also very beneficial for the science of gravitations and general relativity. So on this note, I will leave the floor, and I will be happy to take questions. Thank you for your attention.
All right, excellent. Thank you so much, Maxime, for that incredible talk on the mysteries of black holes. We really appreciate you sharing your time and knowledge with us tonight. I mean, personally, it was an amazing presentation, and of course, the black holes topic is always it's a constant hot topic, like in every single stage of the current physics. All right, well, If you don't mind, we have got a few questions lined up for you. Let me ask first. First of all, the first question is, when two black holes merge together, what happens with their singularities mathematically?
That's a very good question. So first of all, let me a word of caveat is that this is a situation, the black hole merger that is, simulated on computers, but mathematically, this is still something that we are investigating. If you were forcing me to make a conjecture, I would think that, when two black holes merge, the end state should be a rotating Kerr black hole, at least up to some corrections, right? But okay, those corrections, I think they're probably quite similar to the ones you have when you have a single black hole. So if I were to venture a conjecture, I would think that the singularities that is inside the resulting black hole, the final black hole, is probably the same as you would get if you perturb a Kerr black hole. Therefore, the ones that I showed in my slides. So meaning that you have a weak singularity, which is, which you can call an inner horizon, actually, and a stronger singularity, which is space-like. So that would be my conjecture. But it could be the case that once you start doing some mathematics on this, the conjecture are defied, and then it's much more interesting than we thought. So who knows? Ask me again in 10 years.
Wow, pretty interesting. Thank you so much, Maxime, for that. I also got another question, also regarding the math behind black holes. So, do you think that we are missing math in order to finally solve all the gaps within the black hole's mathematical analysis?
Yeah, thank you for the question. So I think as far as classical general relativity is concerned, I think we don't. So I think we have all the mathematical tools. And in fact, I think these mathematical tools have really brought some answers that were counterintuitive even to some physicists, and have really settled some points that were points of controversy. So, for example, regarding the singularity inside a black hole, it was previously thought that all singularities are space-like and look like Schwarzschild. And in fact, thanks to mathematics, we've seen that this is unambiguously false. In fact, if you perturb a rotating black hole, the singularity is null, and it's weaker than Schwarzschild, at least for parts of it. So there are some questions in which mathematics have completely changed the physical picture that was that was there before. Now you're asking what are the mathematics we're missing. So I think we're still actually, unfortunately, lacking a mathematical framework to understand the effect of the quantum effects on a black hole, especially near singularities. I think there's still some mathematical formalism to be developed, which is still more models than a complete formulation of quantum gravity, which I think we're still far. But even trying to understand this is not completely done. But there are recent progress. There's recent progress that make me think that we're getting there. So in summary, for classical problems, there are still mathematical results to be proved. Not everything is done, but at least the formalism is there. For the further question, we don't yet have the formalism, but I'm optimistic that we will have it soon, and then we can start doing some mathematics, and this will go on for many, many more decades, I'm sure.
All right, excellent. Yeah, hopefully we're going to get into that mathematics soon. Right, excellent. So now we can move on with the next question from Zach.
Hello, Dr. Van de Moortel. Thank you for your very interesting talk. My first question is, when talking about the roles that the dimensions of space and time take inside the event horizon of a black hole, what is meant by time and space swapping roles?
Yeah, thanks. That's a very good question. This is something you often see in textbook, in fact. I think it's a bit of a misconception, which has to do with what I was telling, which is we think of in terms that are too Newtonian, actually. So the point is that if you take, so the point is that general relativity is a geometric theory which does not depend on coordinates. Right? But if you take coordinates, let's say on a Schwarzschild black hole or any very well-known spacetime, you see that the coordinate which denotes time in the exterior, which is t, becomes a space coordinate in the interior. Okay, and so this is what people mean when they say that time and space switch role, because what was before a space coordinate becomes a time coordinate, and what is before a time coordinate becomes a space coordinate. But the moral of the story is that you should not rely on coordinates. I think this is so. In reality, there's no such thing as time and space swapping roles inside a black hole. I think I really want to say that, and thanks for the question, really, to allow me to clarify this point. Coordinates are meaningless in reality. There's still a sense of time and still a sense of space inside the black hole, and it's not different from the sense of time and the sense of space outside. And for that, this is exactly to answer this kind of question and clarify such confusion that you need mathematics. You can make sense of what it is, for example, for a vector or a curve to be time-like that would represent an observer, and it's the same inside the black hole and outside the black hole. That makes sense?
Yes, thank you for your very insightful answer to that question. My next question is about the nature of the Kerr singularity inside of a rotating black hole. Is the singularity is commonly described as a ring? Is the ring shape solely a consequence of angular momentum, for example, due to like frame dragging, or are there other contributing factors?
Yeah, thanks for this question. So this is also one of my pet peeves, actually. So the only question, the question, that is important to understand is how do you obtain that ring singularity? So in short, my answer, which is maybe a bit provocative, is to say that there is no such thing as a ring singularity. So I only trust, and not even fully, but I would only trust the Kerr black hole up to the inner horizon. Let me tell you why. The way you define the Kerr black hole is, as you define any solution generativity, you specify its initial condition, okay, at time equals 0, and then you solve the Einstein equations. Okay, so this is sort of how I think it's useful to think of generativity, a little bit like in Newtonian mechanics. If you specify initial condition of, let's say, an object that you throw, then you will have the whole trajectory. So this is something, that is, very simple, but very prevalent in our way to think about generativity mathematically. And if you do that, you would see that if you specify the initial data for Kerr, you would see that the evolution starts at the inner horizon, which is why it's called a Cauchy horizon. And therefore, you should probably not trust what is beyond that inner horizon. So how is it constructed? Well, it's just a coincidence that if you take the same expression, towards the inner horizon, you take the same expression, you can continue it on the other side of the inner horizon. But mathematically, when you're continuing this expression, all you're doing is an analytic extension, which does not, in my opinion, and the opinion of the mathematicians working on this analytic extension doesn't have any physical meaning. So I think the real question to ask about the Kerr black hole is, is that of the inner horizon. And then let me connect to your question. The very presence of the inner horizon is indeed due to the angular momentum. So the presence of angular momentum changes dramatically the structure of the black hole interior, because for the Schwarzschild black hole, which does not rotate, you have the singularity. And here the inner horizon is not singular. So this is something completely different. And this is a long story, that actually Roger Penrose himself started, that goes under the name of strong cosmic censorship. So let me stop it there. I hope the answer makes sense. If not, I'm happy to elaborate.
Yes, thank you so much. Let's move on now to our next set of questions from Anidia.
Hello. I loved the presentation. It was amazing. I got to know like so many things that I've had on my mind. So thank you for that presentation. My first question to you is a bit philosophical in some sense, a bit physical in some sense. So what's the difference between a horizon and a surface? Like, is this horizon a real place or is it just like a boundary in space-time?
Yeah, so this is actually this is a great question. This is actually where the mathematical terminology is useful. So the event horizon. So let's talk about what is a black hole. A black hole region is a region of space-time from which you cannot send light to infinity. This is the mathematical definition. It's a very simple definition, but it's a mathematical. And now you can talk about the boundary of that region. And that is the event horizon. And as you correctly point out, this is a hypersurface, meaning that it has 3 dimensions, okay? And so as to the question whether it's a real place, so that's also an excellent question. And then it depends on what you mean by real. So if by real you mean observable, the answer is no. It's not observable, at least not locally observable. Because if you cross the event horizon, you would not know that it is an event horizon. This is different from what is called an apparent horizon. So an apparent horizon is a measure of, it's a location in space-time where light, if you want, bounces back and goes back in, This is not the same as an event horizon. It's two different things. But this one you can measure, the apparent horizon. The event horizon you cannot. So in other words, and to quote a very famous physicist who said this, there could be an event horizon growing in this room where we're talking right now, and we wouldn't know about it. Maybe we are at the event horizon of some black hole. You don't know. But if you were the apparent horizon, you would very much know. So in a sense, okay, it's real in a sense that you can make sense of it mathematically, and it is indeed, a surface within space-time, a concrete surface, right? So you can make sense of it. But if you personally were crossing into the black hole, you could not tell that this is an event horizon. You need to know the whole history of the black hole to know where the event horizon is. Maybe that's another way to put it. I hope that makes sense.
That's a pretty good answer. I heard that there was like a conversation between Oppenheimer and Einstein that happened, where Einstein's main problem was that how would you tell if you have crossed the event horizon? And that's what Oppenheimer came up with. Like you can't tell if you are away from the black hole.
Yeah, I didn't know about this conversation, but I think that's consistent, and this is consistent. That Einstein would be very bothered by this.
All right, so moving on to my next question. It's a bit mathematical question for you. So if Einstein's equations are time symmetric, how come black hole dynamics exhibit irreversibility?
Well, so yeah, this is related actually to the conversation about the event horizon. This would be my answer, because this is really once you form a trap surface, once you form a black hole, let's say, that means that you cannot send light to infinity, and this property will remain in the future by definition, right? So in a sense, so this is, in that sense that it is irreversible, if you want. Of course, you can do, the opposite, and sort of go backwards in time, and then instead of having a black hole, you would have a white hole. But so on these white holes, there are several things I want to say. So first of all, it's not clear what is the physical process by which they would appear. Second of all, they are probably unstable to perturbations. And third of all, these white holes, maybe you can think of them as cosmological models if you want. So there is, okay, to answer really your question, there is, yes, the Einstein equation are time symmetric. You can reverse time and instead of a black hole get a white hole, but that doesn't mean that the white hole is necessarily a physically relevant object. I hope that makes sense.
Thank you for so much for your answer. I would like now to pass the stage to Danielle, who would ask her questions.
Thanks, Anidia. So my first question is, what are the biggest remaining mysteries about black hole formation that researchers are currently trying to solve?
Thanks. That's a great question. So I think so. The two main mysteries I would mention about black holes are that of cosmic censorship, in fact. So why do I say it's two, even though I just said one thing? Because there's a weak cosmic censorship and there is a strong cosmic censorship. And so what does, the weak cosmic censorship tells you? It tells you that you cannot have a naked singularity. So in other words, if you have a singularity, it must be inside a black hole. That's a weak cosmic censorship, in a sense. Now, the strong cosmic censorship, you can think of it, I like to think of it as the converse, the reciprocal, if you want. So meaning that if you have a black hole, then there must be a singularity inside. And these two things are complicated precisely because if I state them in such a radical way, they are false. So they are naked singularities, mathematically they exist, and there are also black holes without singularities, they also exist. But the point is that the naked singularities are unstable, that's what we believe, we're trying to prove it, And the black holes with no singularity, they are also unstable. That's also what we're trying to do. So in a sense, I would say if I had to narrow it down to two mysteries, I would choose those two, the weak and the strong cosmic censorship. And basically, okay, this is a fancy name to say we're trying to understand, one, how black hole forms, and two, what are the singularities inside black holes. These are some of the big mysteries.
Okay, that's really fascinating. Thank you for that response. My next question is, what might the study of black holes teach us about the fundamental nature of space, time, and reality?
This is a great question, and in fact, a lot. So one of the reasons why we mathematicians are interested in black holes is that they are really testing arenas for various fundamental concepts about gravity. So let me come back to the strong cosmic censorship conjecture that I mentioned. So in fact, this is a conjecture that is about the very deterministic character of general relativity. Let me explain. So remember that the strong cosmic censorship says essentially in every black hole you have a singularity. This is basically what it says. What would happen if it's false? Okay, what would happen if you have a black hole without a singularity? Then you would ask, what happens to observers that fall into the black hole? Okay, so how does that work? Well, think of observers, as you would normally, in the Newtonian theory. You pose initial data, okay, for the observers. So, their initial velocity, position, whatever you want, okay? And you follow the observers falling into the black hole, okay? Then they get to the end of the black hole, which, we like to call the Cauchy horizon. That's the end of their Cauchy evolution. The Cauchy evolution meaning the initial value, the evolution through the initial value problem. If they encounter singularity, it's not very nice for them, okay? But at least, the theory says what happens to them. They get spaghettified, they get burned, whatever. But something happens. The theory clearly says what happens. If there's no singularity or whatsoever, then, okay, they get to some kind of terminal boundary, and then the theory is unable to say what happens. And I think this is very, very problematic. So this is in fact what happens. So this was a question that was asked to me by, I think it was by Zach actually, about the ring singularity and the Kerr metric. So for the Kerr metric, there's exactly this problem. So the Kerr metric is a rotating black hole. It has an inner horizon, okay? And once you have an observer that gets to that inner horizon, what happens to it? Well, you will tell me it goes to a ring singularity, but you don't know that because you made a choice to extend the Kerr black hole after that. And that choice is not canonical. You can make thousands of other choices. So in other words, this particular observer, if strong cosmic censorship was false, this particular observer would be unaccounted for. You don't know what happens to them. So that means that general relativity is not a deterministic theory, does not predict what happens to its observers, and it's a disaster. So, these problems, even though, they are both mathematically motivated because, to be honest, are very cool mathematics. They are also physically motivated because we want to understand, what's inside a black hole. But they also are, fundamentally motivated because they tell us something about how actually singularities can paradoxically save determinism. And this is something I really like, this reversalist perspective, because singularities in the beginning of general relativity were abhorred. Remember, Einstein rejected black holes on the ground that they have singularities. But in fact, now it is the absence of singularity, which in my opinion is more problematic than its presence. So you have to pick your poison. But the theory that doesn't tell you what happens to its observers, I think is much worse than a theory that has singularities. You can engage in a debate, but that's my answer.
Thank you so much. That was very insightful.
You have been listening to the Alan I. Carswell Observatory's monthly TeleTube broadcast, brought to you by the Astronomy and Astrophysics program, which has been written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Danelle, Anidia, Hector, and myself, Zach. Make sure to leave any comments or questions in the comments section or live chat. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to donate, see our website at yorku.ca/science/observatory. You can always connect with us on Twitter at the handle @YorkObservatory and check out our website for show notes, content, updates, and contact info. Thank you for tuning in. Clear skies and have a good night.